In this lesson, we'll be training a semi-supervised GAN to recognize numbers and photos of house addresses. To get the best performance out of our model, we're going to upgrade our previous GAN to use convolutional networks. The deep convolutional GAN model, typically just called DC GAN, is perfect for this. DC GAN looks the same as the GAN you saw before, with a generator and a discriminator. We'll be using the Street View house numbers dataset, which is much more complex than MNIST. So we'll need to use deep convolutional networks for the generator and the discriminator. Otherwise, it's the same. The generator is trying to fool the discriminator with fake images, and the discriminator is trying to properly classify images as real or fake. Let's look at the generator first. As before, the input to the generator is a random vector, z, usually with something around 100 values. The output of the generator needs to be an image that can be sent to the discriminator. That means we need to upsample the input vector to make a layer with the same shape as the real images. Before, we did this with upsampling in an autoencoder where we resized a layer with nearest neighbor interpolation, then passed that to a convolutional layer. This method of resizing, then convolution, was used to reduce artifacts in the final image. For this GAN model, however, we're going to use what was found successful in the original DC GAN model, transposed convolutions. Transposed convolutions are similar to the convolutions you know and love, but flipped. With convolutional layers, you typically go from shallow and wide layers to deep and narrow layers. Transposed convolution is the opposite. You go from narrow and deep to wide and flat. This is a diagram of the DC GAN generator showing the transposed convolutions progressively upsampling the layers. With a stride of 2, when you move the kernel 1 pixel in the input layer, the patch moves 2 pixels in the output layer. This way you can upsample from the input layer. The new layer size depends on the stride. With same padding and a stride of 2, the transposed convolutional layer will be twice the width and height of the input layer, since it moves 2 pixels in the output layer for every 1 pixel in the input layer. The first step in the DC GAN generator is to connect the input vector z to a fully connected layer. Then reshape the fully connected layer to 4x4 by 1024, or whatever depth you have for this first layer. Then we build the stack of layers by upsampling with transposed convolution. Each layer is doubled in size using strides of 2, while the depth is halved from 1024 to 512, for example. The final layer, the output of the generator, is a 64 by 64 by 3 convolutional layer. The size of this layer is actually whatever the size of your real images is. So if you're using the Street View house numbers, then it's actually 32 by 32 by 3. And again, 3 is for the 3 color channels, RGB. You'll notice there are no max pool or fully connected layers in the network, just convolutions. In the generator, the authors used ReLU activations for each layer. They also used batch normalization on all layers except the final one. Batch normalization scales the layer inputs to have a mean of 0 and variance of 1. This helps the network train faster and reduces problems due to poor parameter initialization. We'll cover batch normalization more later on. The discriminator is a convolutional network with one fully connected layer at the end, used as the sigmoid output. Notice that unlike most convolutional networks you've seen, there are no max pool layers. The downsampling is done completely with the strided convolutional layers. The final convolutional layer is flattened, then connected to a single sigmoid unit. Again, the layers have leaky ReLU activations and batch normalization on the inputs. The rest of the implementation is the same as the GAN you saw before. It's just the networks that have been changed. Next up, you'll learn more about batch normalization and apply it to the GAN you trained on the MNIST dataset. With batch normalization, you'll be able to create deeper networks for the GAN and get better results. Cheers.